Thank you for the brief stall. Hello, everyone. I'm Allison Cox from the University of Dayton Research Institute, here to talk about a new material from 3D Systems that we evaluated for interior cockpit components. So I'm sure many of you are familiar with 3D Systems, and I'll let them talk about themselves at their own booth. But if you're not familiar with UDRI, we are a contract research company attached with the University of Dayton, but we are fully funded off of contract research, focused on applied research, material characterization, really geared toward the aerospace and space application industries. I myself am a part of the Additive Manufacturing Technology Development Group, and here we focus on TRL levels 4 to 7 from a variety of different printing techniques involving polymers. We manufacture our own laser powder bed system so we can integrate and iterate on new materials or sensing capabilities. And we also have our own ultra-fast laser technology team, so we can really attack applications that our customers bring to us very quickly. Within UDRI as a whole, we also have a variety of testing capabilities in-house. So that makes programs like this happen very quickly, where we can iterate pretty cheaply and quickly on materials as we develop them with third-party partners like 3D Systems for our aerospace customers. This includes a variety of mechanical testing, ASTM standard testing, and one that I'd like to highlight specifically today is our Flame Science Lab with 30 years of experience within the flammability realm geared toward aerospace applications. So as an overview of this program, we researched this material for about 1.5 years with 3D Systems, partnering on a program that was funded through America Makes. The overall objective of this program was to identify a material that meets modern flammability specifications, but also is rigid and robust enough to withstand installation and use for interior cockpit components. So we achieved this in 3 main steps. First is to work with our aerospace customers that are identifying these as need parts to identify the modern flammability specifications as laid out by the FAA, and then also identify what kind of material properties we're looking for in the, quote, rigid components. Then take those requirements we develop and hand them over to 3D Systems so their material experts can develop materials for us to evaluate. And then finally, when we've completed our testing, move those materials back to our customers that stated their need, and then work towards implementation and transition into aerospace parts. Now, for a few years, there's been a need in the aerospace community for a material that can survive installation and use within the aircraft, specifically with these knobs and small panels or switches that you see riddled throughout aging aircraft that is still flying, but these small parts might be breaking or becoming brittle with decades of UV exposure, heat exposure, people handling them a bit roughly, and they're breaking, and there's no current pathway for replacing these parts in the market today. It's usually cost or time that inhibits the replacement of these parts successfully. So this is really a key application that additive can really make an impact. However, in the past, UDRI, in conjunction with 3D Systems and our aerospace partners, have identified this material gap that exists. First, there are plenty of FR materials that exist on the DLP market. However, many of them only pass modern flammability requirements at very large thicknesses, or they're very brittle. So we're talking around 2 to 3% elongation, which does not survive even the main installation of small parts like this. And then any part that is tough enough for installation does not meet modern flammability requirements. So having identified this kind of gap that exists in the market, we partnered with 3D Systems to kind of tackle this specific hurdle so we can start manufacturing reliably parts for aerospace sustainment. So throughout the program, we evaluated about 7 material candidates from 3D Systems, and all of those were manufactured at 3D and then given to UDRI to independently test, evaluate, print, and post-process all on our own as a third-party evaluation. And here's kind of a very overwhelming but comprehensive summary of the testing that we performed. Again, all of these tests that we did were very specific to this application. There are more tests that have been done for the material itself on the 3D system side. But I want to call out these two main material requirements that we were looking at. So like I said, these are the two material requirements that currently did or previously did not exist, but now we are seeing both a passing of modern flammability requirements and also a high elongation of 33% compared to the 2 or 3% that currently exist on the market in other materials. So this is a very unique combination of material properties that makes this key for these applications. So to kind of dive deep a little bit into what these flammability specifications are, because I think this has larger implications onto the DLP and SLA part replacement field as a whole. So a lot of people refer to FAA or flame, smoke, and toxicity testing as one giant umbrella of material properties that we need to pass. However, the material properties that are needed are often dependent on two major things. First, the size of the part that you're trying to replace and where that part is within the aircraft. So for example, larger interior panels or structural components require the very difficult to pass 60-second vertical burn test, and you often also have to pass stringent smoke density, heat release, or toxicity testing as well. However, when we're looking at small cockpit components, anything printed on the figure 4 size of materials that we're replacing, we really only rely on the 15-second horizontal ignition test, or sometimes even the more stringent 12-second vertical burn test. So what's really important within the aerospace realm is to clearly identify what part you're trying to go after and what specific flammability requirements are actually required for that test. So we can clearly identify that here. And as a result, after identifying what tests we're actually going after, we can reliably test that for our materials. We did this, again, all independently within UDRI's Flame Science Lab. And with the material candidate from 3D Systems, we are reliably passing the 12-second vertical burn test at 2 millimeter thicknesses, which is very adaptable for the small materials and parts that we are actually going after. So this, again, this tough FR V0 material that's newly released by 3D Systems is passable on modern flammability specifications for a variety of figure 4 size parts. In addition to just flammability and just elongation and toughness, we also had a variety of other material and performance properties that our customers wanted us to look at. So first is UV exposure. To simulate the kind of cockpit environment, we expose these materials to UV light through window glass for 600 hours of accelerated weathering and saw no major cracking, crazing, or discoloration that you would usually see in major UV degradation. We also evaluated paint adhesion. For many of these small knobs that are going in the cockpit, we had to meet a very specific paint requirement, and we wanted to make sure that wasn't going to rub off or get nicked and start chipping off, and so we were able to pass paint adhesion tests very well with this material. And then finally, we looked at fluid immersion of tensile bars in various both cleaning fluids for figure 4 parts like IPA, but also hydraulic fluids, turbine oils, etc., of what you would actually see in an aerospace market with no major change in our tensile or elongation. Any changes we do see, for example, with the turbine oil on elongation, that's not really affecting our performance of the part, but it is reported to our aerospace customers so that they can know what to expect if there is something that occurs with a fuel or oil spill with these parts. So with the success of passing modern flammability requirements and having a tough material that kind of is a new and innovative material on the market, our customers also turn to the potential of electroless plating of these parts. Electroless plating is when you take these plastic parts and add a very thin metallic layer to them. It's commonly seen throughout the automotive, aerospace, and even rail industries to create lightweight parts, but maybe even a higher mechanical characterization because of that addition of metal and also a kind of better look to the part. So we know that this can add mechanical properties, but what's not really explored is how that affects our flammability requirements. Do we pass higher? Does something catastrophic maybe happen and for some reason we're not passing our modern flammability requirements anymore? So on this program, we were able to dedicate some resources to find out, again, in partnership with both Repliform and our Flame Science Lab. As a result, we not only are passing the same 2 millimeter thickness of 12-second vertical burn, but we're passing the much more difficult 60-second vertical burn test with no afterflame, no afterglow, no drip in the material, which really means that we are not adding or propagating the flame anymore, which is what our aerospace customers want to see in any of their materials that they're putting on their aircraft, and specifically with novel materials that they're using for part replacement. Obviously, you can see this is a very interesting passing. We have a kind of ballooning effect happening to our material. And what's actually happening is that very thin layer of metallic film is containing any spread and at pyrolyzing the material within the metal film. But really, that's creating a char, and again, not contributing to any flame or flame event within the cockpit. So it's still considered a pass according to the FAA. And as expected, we're also passing and increasing our mechanical properties, UV exposure, and lifetime as well with metal plating. So this kind of opens the door to potentially larger parts. Again, metal plating is not required to pass any of these modern flammability requirements for figure 4 size parts, things that are smaller, like these small panels or knobs that we've frequently explored with our aerospace customers. But perhaps we might be looking at larger parts, larger panels that might be unlocked on SLA or perhaps even 3D Systems' upcoming PSLA technologies, where we're looking at larger parts. This 60-second vertical burn or toxicity and heat release testing will be required, so this could be an open door into those applications as well. So towards the end of our program, we also looked into a specific case study. So just as a quick overview, another group, a sustainment group at UDRI, was brought this problem where they needed rapid part replacements of these very small knobs. These were commonly breaking on aircraft, and there was no viable way to reproduce them. And many of the technicians actually even had to go to Home Depot just for a quick fix to get the plane back up in the air, which is not how we want any of our planes flying. So obviously our group turned to Ultem 9085. This is a common material and aerospace ready. However, the customer was pretty dissatisfied with the part quality. Obviously, they printed as expected, but if you're looking at small parts like this, FDM really doesn't give you the best surface finish. So then the sustainment group turned to different post-processing methods like sanding or different coating technologies to kind of get it very smooth. The customer was familiar with DLP parts before and kind of wanted that surface roughness or surface smoothness actually. And we were actually able to add in this material that we had just confirmed passes modern flammability requirements and is tough enough to survive the installation of use of these materials that would have to be threaded onto metal components. And we threw our parts in for evaluation. So on this chart, you can kind of see this was made by the customer themselves, rough to smooth, which obviously we're outperforming any of the FDM with the DLP technology, and then complex to simple. So this complex to simple includes print time, and specifically the manual labor after the print time in order to get that desired smoothness. So this material is not only are we confidently passing modern flammability requirements, we're tough, but we're also outperforming some of the common and trusted aerospace ready materials, meaning that this material, I'm confident, is ready for that next step of qualification and implementation into aerospace customers. So as kind of a final summary, this material, the tough FR V0 Black from 3D Systems, meets modern flammability requirements while maintaining high elongation, making it ready for implementation in the aerospace market. We've seen that plating increases the mechanical properties of this material, but we've also proven that we can achieve a higher flammability requirement, making this possible for larger platforms. We are ready for qualification, so whether that's Air Force circulars in the future or other different qualification documents to really establish confidence within the aerospace market that this material can solve their needs of today. But we also demonstrated that we can not only solve the materials by direct replacing the knobs or switches or components as given to us, but we can also use the digital tools within 3D Systems software to add in lettering or to add in texturing, so we can really cut down on those post-processing steps of painting or adding in numbers that are part of the traditional manufacturing of these parts. And we can also look into future applications instead of just sustainment. So this unlocks potential applications with drones or satellites, specifically when we start looking into those larger parts, which kind of leads to a larger conclusion of not only is this material available and ready currently by 3D Systems on the Figure 4 platform, but another material that shares similar chemistries with this is available on their SLA platform as well. So throughout this program, I've kind of alluded to using plating to achieve higher flammability requirements for larger parts. And now that's possible on the SLA platforms as well. And we can start looking at larger panels or structural components that might be needed for either current aerospace applications or future drone and satellite applications. So that's the conclusion for my program. I'm willing to take any questions, and I'll be hanging around, and I'm sure 3D Systems is willing to take any questions, and they have this material at their booth as well if any of you have any more questions.
Thank you very much.
Thank you.
As a relatively frequent flyer, I was a little concerned about what happens to the knobs and dials when they break, and I didn't want to ask. And then you said people go to Home Depot, and I definitely didn't want to know. So I'm very glad that you're doing this work to get aircraft back in the sky with the correct controls in place. That's very good. Anybody, any questions, either for Alison or for 3D Systems at this point? If not, come out of here, turn right. The 3D Systems booth is just down at the front.
Thank you for your presentation. I just wanted to ask, how do you characterize the quality of addition with the electroless plating?
The quality of, excuse me?
The addition between the metal and the polymer?
So we've mainly just looked at the flammability. There's a lot more to look into on kind of resilience of a plated polymer test. Usually it adheres quite easily. Usually electroless plating is done on conductive materials. So instead for polymers, we kind of had to add 2 conductive elements to it to plate it. If you're looking at larger applications, there's still more research into how that affects the polymer material underneath. But so far, we're confidently passing flammability.
And I just wanted to ask, for the FDB thick epoxy, so do you just put a coat of thick epoxy on the FDM printed part?
Yeah, that team just looked at different coating techniques. So they just put epoxy and maybe even sanded it down a little bit. But still, that wasn't getting as smooth as printed DLP parts.
Thank you.
Thank you.
Anybody else? No?
Thank you.
Thank you very much.